Gibbs-Duhem equations and so on. But from one expression for the excess Gibbs free energy, it is applicable to whether you are going to develop it for a binary mixture or a ternary or higher order mixture. So what we are looking at is that this expressed as a function of m1, m2 and so on, and of course p and v, and then we can show that RT log gamma I equal to 1 to c is given by v GE by E Ni. Or as some would write it, if you want a direct expression for logarithm of gamma I, then I have to. Just as we saw for the partial molar quantities, whatever applied for the partial molar quantities will apply for effectively log gamma I or RT log gamma I, depending on which one you are going to differentiate with respect to GE or GE by RT. So let's take one of the expressions given. Here E by RT is given for the landlog model. A x1 x2 by A by B x1 plus x2. This is what is given. So if now I differentiate, so there are two options. One is converted to n1 and n2. In this case, that will turn out to be the easier option. So far we have dealt with polynomial expressions for the extensor property. So it's easier to properly differentiate that with respect to the mole fraction. But here it is not quite in the ratio of polynomial. So first I do the first option is to convert it to GE. That means I have to multiply it by n. N. So n is n1 plus n2. This is not going to be helpful. I have to convert it to n1 and n2. So I am going to differentiate the extensive property. Then I have to convert it to mole numbers. A is here and B are, I guess, taken to be a constant. So looking at model for GE is effectively proportional to RT, and pressure dependence we completely neglect. So this is n1 plus n2. A n1 by n1 plus n2 and n2, and then I have A by B n1 plus 2 by n1 plus n. So I can cancel this, one of them. So I get A n1 n2 divided by n1 plus n2. And then we are further having to divide this by, if you look at this, I can take n1 plus n2 as a common factor. So what we effectively happen is we are going to divide. So we get b times n1 plus n2, b times n1 plus n2. Then I am going to make this as a n1 plus b n2. So divided by, we have to make sure that we don't miss out any n's. The basic idea is this now has the following form. One thing you have to check, because there is a lot of talk about how any model should satisfy the Gibbs-Duhem equation. We can check whether any model for the excess Gibbs free energy is going to lead to gammas which will satisfy the Gibbs-Duhem equation by checking if this is actually an extensive property. If this is to be an extensive property, then it should satisfy taking the RT out of it, it is better. Whether this is being satisfied or not, you have to check. If this is satisfied, then the gammas that you find, if you do it correctly, will satisfy the Gibbs meter. That's a differential condition. This is going to be easier to check. You can very easily verify that this will be satisfied. So you find in some chemistry textbooks especially, you have equations for the extensive properties which don't even satisfy this basic idea, and of course they are using it as an empirical expression. But even an empirical expression has to satisfy certain basic rules. With an extensive property, it has to be homogeneous of order 1, the extensive variables. So that is clearly satisfied here. So now I can differentiate this. So this is GE by RT. So if I take by dN1, so I will differentiate it with respect to N1. So I have A N1 plus B N2 the whole square, and then I have A which can be taken out as a common factor. So I have A N1 plus B N2 times derivative with respect to N1. So you cannot forget N2. N2 can probably be taken out 2. Anyway, let's leave it as it is. Times N2. Numerator I have N1 times N2, and I am differentiating with respect to N1. Then minus N1 N2 is the numerator times the derivative of the denominator, which is simply A. So clearly you can see A N1 N2 will cancel, and you get this A B squared N2 squared by A N1 plus B N2 the whole square. So at this stage, again there should be a check. Now I have got expression for gamma 1 or logarithm of gamma 1. It must be expressible in terms of the mole fractions alone. So we are working with the mole numbers. Finally, when you get to the expression, if you have done the differentiation case, this will help you ensure that you have not missed out some N1 or N2 factor here and there. Right? So that you can very clearly verify. Because if I were to divide, if I to get the expression that is given in the standard textbooks, I would just simply have to divide the numerator and denominator by Bn2 square, B squared N2 square. If I do that, I get A, and this divided by B squared N2 square means I have to take Bn2 within the square. So I get A N1 by B N2 plus 1 the whole square. Now clearly N1 by N2 is simply equal to X1 by X2. This will be A by B X1 plus X2 plus 1. This is the expression that's given. Well, clearly I need to recognize that X2 is equal to 1 minus X1. So I've got log gamma 1 either in terms of X1 or in terms of X2. Only one independent mole fraction is there. So you should be able to verify that. But it's conveniently given because there's a certain symmetry between the expression for log gamma 1 and log gamma 2. Now having got log gamma 1, now there are two methods to obtain, three methods in fact to obtain log gamma 2. I'll just outline those methods. The easiest would turn out to be simply take the derivative with respect to N2 and you will get log gamma 2. It is not equal to this, it will be something else. Right? So I have the expression for dE by RT, and instead of differentiating with respect to N1, if I differentiate with respect to N2, I will get that. Now another method, I am now going to write log gamma 2, the expression for that without any proof, simply by inspection of the expressions for the corresponding partial molar property. If you look at the partial molar property of component 2 in a binary mixture, right, the expression here would be GE by RT. That's the analogous specific quantity, but I'm just dividing by RT. And then minus x1 E by D x1 of GE by RT. You have to convince yourself that this makes sense. If you are confused about this, then just make this RT log gamma 2. So this is just the RT log gamma 2 together represents a partial molar property, and this is a specific excess Gibbs free energy. And if you go back to the partial molar property of component 2 in a binary mixture, you would see that this would be the corresponding specific quantity. Either volume, or if you take enthalpy of energy, it's better because this is also has the units of energy. Instead of that, you have the excess quantity, and then minus x1 d by dx1 of the specific quantity. That is the formula for the partial molar property of component 2. So I'm applying that directly here. Right? Now you will see that we can do it, but first of all, GE is here by RT is given by AX1. So first I have to express this in terms of x1 only, because that's what I have to differentiate with respect. I will just outline that, and it's a good exercise, even though it will be somewhat long-winded. Good exercise for you to complete that. So now AX1 times 1 minus. So the new denominator, of course, will have a B will come in the numerator. So AB. The denominator, if you want to express it in terms of 1 minus x1, so that would be A minus B times x1 plus B. This is 1 minus x1, right? So ax1 minus bx1, and then I get another b. So this would be a minus bx1 plus b. Now, first I need to get this, then I have to combine it with this. So you can see it's going to be a somewhat tricky situation, but it can be done. If we're going to do that, so this would be a minus b times x1 plus b, the whole square. Then I have a minus b x1 plus b times ab again can be taken out, and this is the derivative of x1 times 1 minus x1 is 1 minus 2x1. Then minus x1 times 1 minus x1, and I have to differentiate this with respect to x1. That's easier to do. That is simply a minus b. So this is what I have. Obviously I have to simplify this. I probably work by simplifying it here itself. So quite a few terms might cancel out. Okay, so let's just try that. Okay? AB by, I'll just put this as the denominator. The numerator, if you see, it has here a minus b times x1. Let us split it. Then minus 2 x1 squared times a minus b. Then I have plus b minus 2b x1. And then this would be plus x1 squared times a minus b, dividing one of the terms, and then minus a minus b times x1. And so we can see that clearly a minus b and this gets cancelled. Right? And so what I have is ab by the denominator times x1 square plus x1 square. This will be minus x1 square times a minus b. Numerator is also in terms of a polynomial in x, and is a ratio with respect to the denominator. It's also a polynomial in x, right? Minus x1 square. And that's not all. So now I have to multiply this by x1 and subtract that quantity from GE, which is given by that. So it's going to take another set of manipulations, and the final answer. So differentiating dE by RT, so I'll directly get log gamma 2. So log gamma 2, the answer is given in the T, very similar to the expression for gamma 1. So log gamma 2 is given by B divided by 1 plus B over A x2 by x1 whole square. So it looks very similar to this, and you might wonder how this is going to come out of all this. It looks quite complicated there, but it will simplify and you will get that. Now, another way, given log gamma 1, another way to get log gamma is from the Gibbs-Duhem equation, as we have seen in the case of the partial molar property. The Gibbs-Duhem equation in terms of the binary mixture is given by that. We didn't quite write it explicitly earlier, and this is what it will turn out to be. Right? And so this will turn out to be even more complicated. In this case, d log gamma 1, right, I have to differentiate it with respect to x1, and then I have to integrate to get log gamma 2. But it's possible that I might just give for some other model, I will give you log gamma 1 and ask you to calculate log gamma 2 without giving you what GE is. So then you should know how to do that. Right? So this may not be the best example to try it because it does get quite complicated, but you can easily see that the Margules, because I want to point this out, because you need to know what is the limit, just as we saw with the partial molar properties. The limit as x1 goes to 0, the v1 pm or h1 pm will go to the corresponding pure component properties. So in the same way, for example, the Margules is very simple, easy to do anything here. And when here there is only one parameter. Now suppose let's see this is given. Now you can see generally some log gamma 1 is given as a function of x1 or x2, and then I ask you to calculate log gamma 2 without giving you what the GE is. Right? So in this case you can easily guess this is coming from dE by RT. You can go there directly and get the log gamma 2. But if I give this, then we see here this partial and retaining. The partial is not keeping x2 fixed, but rather keeping the temperature and pressure fixed. So you should remember, because when you're differentiating here, for x1 and x2 both appear, it is not as if you're differentiating x1 keeping x2 fixed. That could be a misleading way of looking at interpreting the partial degree. So you who know that what is x1 and x2, right? That makes no sense at all. That is something you have to keep in mind. So I will just write this as, here it is easy to do. So I get x1 times 2a times 1 minus x1 minus, we get, let's say, derivative of log gamma 1 with respect to x1. Right? So then plus x2 is 1 minus x1, and I don't know what log gamma 2 is, equal to 0. Conveniently, 1 minus x1 will cancel. then I get E log gamma 2 by dx1 is equal to A times x1. This is of course very easy to integrate. You can see what integration would be required in that other grand log. It's not that easy, but you can try it as an exercise, you can do it. Right? But here, crucial point is that there will be an integration constant. Even though in this case it will turn out to be 0. Log gamma 2 is A times x1 square, which we know is the answer. If you just leave it like this, I won't give you the full marks in a quiz because you have to, this is a constant. Now, how do you determine the constant of integrations? So, we have to first look at how the gammas were introduced, because we introduced the gammas through the chemical potential, but we know that Fi means for any component, the fugacity of any component in an arbitrary mixture, not necessarily an ideal gas mixture or ideal. This is one way of writing the gamma, or expressing the gamma. Is gamma I times xi times Fi. So Fi is the pure component fugacity of component I. We have seen because we introduced the gamma through the as exponential. We define it, some books define the gamma as a ratio of Fi mixed to xi Fi. So then automatically, from the definition of the ideal solution, right, we know that the gamma for the ideal solution is 1, and you regard the gamma as how much the actual mixture deviates from the ideal solution. But the way we define it was through the chemical potential. Gamma I actually in terms of the fugacity will actually be given by this expression. Now you can clearly see that. Let's now take so what will happen when xi goes to 1? This is now valid for any arbitrary component mixture. If xi goes to 1, right, so this goes to 1. Now, if we look at this, dp, this is a function of x1, x2, and xc minus 1. Right? So, if one particular xi among the c minus 1, let's consider. So, of course, this can be written for arbitrary number of components. You can ask what will happen to the c component, that we can consider separately. But this is in general a function of temperature, pressure, and the mole fraction. Whatever it is, we should be explicit in terms of x1 is a particular component which makes whose mole fraction is going to 1. All other mole fractions are going to 0, right? So what will happen is this will become 1, right? And clearly the mixture itself is going to become the pure component I, fugacity. So this will actually tend to, if you look at what each one will tend to 1, this remains as it is. So that is anyway pure component. This will tend to Fi of dp. Because we are getting to the pure component, so in the mixture nothing will be there other than the pure component. So clearly we expect the fugacity of the mixture to become of the component I. The component I in the mixture, as all other mole fractions other than the I mole fraction are going to C1. All the other mole fractions are going to 0, and the mole fraction of component I is going to 1. So clearly this will become Fi of t. So you can clearly see that gamma I will tend to 1. In the limit, as xi goes to 1, I have to gamma I of that component will go to 1. So if here, if I am having log gamma 2, then in the limit, as x2 goes to 1, right, log gamma 2 actually will have to be 0, right? So as x2 goes to 1 means that x1 goes to 0. If you limit x2 goes to 1 of this must actually be 0. Because here I'm using the logarithm of gamma 2. Gamma 2 goes to 1 as x2 goes to 1. Then I will get the proper limit, right? So this has to be equal to 0 because x2 goes to 1, gamma 2 goes to 1, and log gamma 2 goes to 0. Now if I apply that limit here, x2 goes to 1, x1 goes to 0. This will become 0. And so we see that the constant is actually equal to 0. That's something you have to prove. And not simply assume, since we know the answer here, not assume that it will be the case. Right? So clearly from this I can get the, there are three methods I have seen to get log gamma 2. One is by directly differentiating the excess Gibbs free energy total with respect to N2. Another is using the Cauchy-Miller property expression for the component 2 in a binary mixture. Another is using the Gibbs-Duhem equation, making use of the limit proper. Right? But it so happens that in the van log, the easiest way is to just directly differentiate with respect to N1 and N2 and get the answer. Some of the other cases, it might be all methods might be equally simple. So this is one step. So that's the first step. I'm taking van log as an example. So first step when you got the model for the GE is to get an expression for the gammas if you want to use the modified Raoult's law. That is our main objective. We've deviated from that. Right? So we've taken this as an example and shown, and we've given one or two models. There may be other expressions in the literature which are available. Whatever is given, you should know how to get the gammas. That's the main. Now here, though, this is the reverse process that we need, which is, in this case, because we started out with the azeotropic or any other data is available, and you use the data to find the parameters in the model. So if we now look at these two expressions, what I really need, because we now go back to the problem that we were solving. So we were given that the benzene, ethanol, or one of those mixtures. So you can take any azeotropic mixture and try to see some of the parameters of these binary mixtures are also tabulated. The value should approximately match with that. They may not be exactly matching because we're just using the data at one point to get the parameters. So what we have is for ethanol-benzene. The azeotrope is at 1 atmosphere. The azeotropic temperature is, azeotropic composition is 0.44 mole fraction of ethanol. This is where the azeotrope occurs. Now, how are we going to use this to find the parameters in any model? Is we get expressions or values for the gammas. So I'm now going to assume that the modified Raoult's law is valid. Right? So I'm continuing to treat the ideal. So obviously, if we treat the vapor as a non-ideal gas mixture, the way you determine the gamma, the values will be different. So I'm assuming that the ideal gas mixture holds for the vapor phase. Assumption holds. Here I have only two. So By1 is B1 sat, gamma 1 x1, and By2 is B2 sat, gamma 2 x2. At the azeotrope Y1 into the x1 and Y2 into the x2. And so I get gamma 1 is equal to P by P1 sat, gamma 2 is equal to P by P2 sat. So we saw that P1 sat must be evaluated at this temperature, that's the azeotropic temperature, because everything corresponds to a particular point. The gamma is also local, corresponds to a particular composition, namely the azeotropic composition. And then we saw P1 sat was 503.61, and so I get a value, and P2 sat is 519.75. what? Currently I don't have those values. So you can easily calculate and tell me. Oh, here it is 1.509. And this is 1.462. So we pointed out that the gamma being positive means the positive deviation from ideality. So we lead to a minimum volume azeotropic. So now the question is, how do I determine A and B? So here I have gamma 1 and gamma 2 in terms of A and B. But now what I want is B and A expressed in terms of gamma 1 and gamma 2. Now on the face of it, it's quite long because it's a non-linear equation, you have pretty much solved it. But there's a simplification that results if you divide log gamma 1 by log gamma 2. Right? So I will do that now very quickly. Because these expressions are also given in the literature. So that is something that may not always be possible to get explicit expressions. It may have been numerically solved for the parameters. So what I mean here, but here it will turn out to be simple. So I divide. It's not log of gamma 1 by gamma 2, but log gamma 1 divided by log gamma 2. Let's see what we get. So we get A. What I'm going to do is I'm going to do it here itself. Right? Let's look at this. This is also log gamma 1. So we get AB squared. And if I divide 2 by n1 plus n2 squared, the numerator and the denominator, you can clearly see that this would be AB squared x2 squared divided by ax1 plus bx2 squared, right? In the same way, this will also can be written as ax1, so this would be ba squared x1 squared by ax1 plus bx2 squared. So when I divide this, I will again get ax1 plus bx2, that means it cancels out. Divided by a square x1 square. Right? So now this will cancel. And what is interesting is that log gamma 1 by gamma 2 turns out to be b over a times x2 by x1. Now you can ask how in what way this helps. But if you look at this, that's what I have. bx2 yeah, so b over a x2 by x1 square, right? So this would mean, but if you look at this, if you look at the earlier way of writing the this is a over b x1 by x2, right? And this would be b but it's always bx2 by ax1 is appearing in the as a group, right? So now what I have is I'm going to find bx2 by ax1, that group of terms is going to be given by log gamma 1 by log gamma 2. But I'm not done yet. Times x1 by x2. So now I can write first expression. If I get log gamma 1 would be a divided by, right? Now I want a over b a x1 by b x2. So that is going to be given by log gamma 2 by log gamma 1 times x2 by x1. Just replace that plus. So now what have we achieved? Can I calculate a from this? This obviously gives an expression for a. So all I have to do suppose multiply this. So A is given by log gamma 1 times log gamma 2 by log gamma 1 x2 by x1 plus 1 whole square. Now we are getting explicit expressions for the A and B. And for gammas in the x1 and x2, those are known at a given point, right, in the space. Similarly, B would be given by maybe log gamma 2. These are very standard expressions. Now what we get is 1 plus bx2 by ax1 would be log gamma 1 by log gamma 2 times x1 by x2 square. That's what I want. So now I have to go back and calculate. I've got gamma 1, gamma 2. And so I have to calculate log gamma 1, log gamma 2. And I know x1 is 0.44. So x2 is 0.56. So I have to substitute all of that and I get A and B. Now if you go to another, so the three suffix Margules equations, they are fairly easy to solve. So you get two linear equations in the two, but you can apply the same idea to the other one, three suffix Margules. But Wilson may be a bit too complicated. So you can do the same procedures for that, and then you can get those parameters A12 and A21 or whatever. So in this case, A turns out to be 1.9461 and B 1.3917. So now you go back and look at the expression for both. You see that both A and B are positive. So what that means is, now let's see if you can get anything from, yeah. So this is squared. So whether this is whatever it is, because log gamma 2, the sign is not fixed. If gamma 2 is less than 1, that would be for negative deviation from ideality. Log gamma 2 would be negative, but then gamma 1 would also probably be less than 1. And so anyway, but whatever it is, whatever happens to gamma 2 and gamma 1, this thing is squared, right? So here for the Van-Leeuwen parameters, I can see the sign of A. Let's look at it here. This is squared. Whatever happens inside, it's going to be positive. So the sign of A is entirely determined by log gamma 1. In this case, both log gamma 1 and log gamma 2 are positive. So the sign both A and B turn out to be positive. Clearly, we have negative deviations from ideality, where log gamma 1 and log gamma 2 would both be negative for a binary mixture. Then you can see that A and B are going to be negative. So you should not be concerned if the A and B turn out to be, the parameters turn out to be negative. That is it. So this may be a direct indication. If you look at what GE by RT is, now I am giving another interpretation of the positive deviation from ideality. This is probably more the first thing that you look at, because before you even calculate the gamma, the GE is given, and let's say the parameters are given A and B, right? So the Van-Leeuwen model, what I have is A x1 x2 by A by B x1 plus x2. In this case, for binary, one parameter is negative, other is also going to be negative. It can also be shown, right? So clearly, so there's nothing that's going to happen here. A is negative, G is negative. So if A is positive, G is positive. So since A is positive means effectively we've already seen that gamma 1, if you use this definition, the gammas have to be greater than 1 for positive deviation from ideality, then clearly GE by RT is greater than 0 for positive deviation. This is another way of, and E by RT. So what is GE by RT? GE is nothing but G minus G ideal solution. That is the excess. You have to keep that in mind. Right? So GE by definition. So what another way of interpreting the positive or negative deviation is when the Gibbs free energy of the actual mixture is less than its ideal solution counterpart, that is, if it behaved like an ideal solution, right, then it is a negative deviation from ideality. The excess Gibbs free energy is positive. That means if the free energy of the mixture is actually greater than that corresponding to the ideal solution, then it can be regarded as a positive deviation from ideality. Another interpretation that is normally given is in terms of the bubble pressure. If you look at the bubble pressure, the expression for the bubble pressure, we saw that even with the modified Ravi's law, you will get an explicit expression for the bubble pressure. It's like that. So obtained simply by adding the two expressions. Given that of E. So bubble pressure means temperature is fixed. So I am going to fix the temperature, and also the X is fixed, right? So bubble pressure would be the way P depends on X at a particular temperature, right? So I am looking at given temperature P versus X or Y. So bubble pressure means I am looking at P versus X. P versus X is actually going to lie above the P versus Y curve, okay, for the pressure. Right? So this would be plus characteristic feature. Now for the ideal, this is my question, the ideal. That's the Ravi's law. First I want to point out that the Ravi's law actually would mean that whatever may be the P versus Y, but the P versus X1, right, is actually going to be linear. This is clearly a linear curve. P2 sand of E plus P1 sand minus P2 sand times X1. It's going to be linear. It depends on which one we plot, which one we turn out to be more volatile component. But actually the way we've plotted it, one would be the more volatile component. So P versus X, this is how it is going to appear. P versus Y may appear like this. There is no constraint on P versus Y, whether it has to be linear or it may not be linear. Okay? But P versus X1 is going to be linear for the ideal case. Now, if this were non-ideal, then for the modified, that is the Ravi's law, linear. Now you have to add a gamma 1. Now for binary mixture, positive or negative means either both gammas will be positive or both gammas will be negative. That's what it will turn out to be. Right? So we see that if it is a positive deviation from ideality, then clearly the P would be what? It would definitely be greater than the ideal pressure. So we can say that if the bubble pressure is greater than the ideal bubble pressure, then it will be non-linear because gamma is clearly introduces a non-linearity. Whatever way it depends on X, when it depends on X1, that means the whole thing becomes non-linear. So the bubble pressure is, let's say, above the ideal, then it would correspond to a positive deviation. If it is below, then it would be a negative deviation, maybe something like this. So, if it is below, then it is going to be negative. That's another way of looking at it. So, we've looked at, at least for the binary mixes, we've looked at three different ways of looking at the positive and negative deviation. One is the gammas will be greater than, all of these correlate with each other, they are all equivalent. Gammas will be, both the gammas will be greater than 1, right? And then the excess Gibbs free energy will be greater than 0 for over the entire composition range for the positive deviation is less than. For the Laar model particularly, the parameters will both be negative for the, so the moment you are given G by RT, and let's say for a particular mixture, here you are given the azeotropic and asked to calculate the parameter. Typically you are given a mixture, parameters are available in the table form. Sandler has a whole table of parameters for various mixtures. Other books also probably have it. By just looking at the Laar parameters, or probably similar things would apply to other models. You can say whether this is going to be a positive or negative deviation. So you can infer from that whether this, but positive deviation does not necessarily mean that it has to exhibit a minimum boiling azeotrope. But if it exhibits an azeotrope, it has to be minimum boiling. The same way negative deviation, for example, Ravi pointed out the deviation is sufficiently negative or positive, it may exhibit an azeotrope. Again, that's a function of the pressure also or temperatures, right? So ethanol water, for instance, exhibits an azeotrope at 1 atmosphere, but if you go to very low pressure, it may disappear. So that cannot be said uniformly that it is going to exhibit an azeotrope at all pressures or temperatures, right? So this is the correlation that you have to keep in mind. We'll just wrap this up in tomorrow's class and go to the next topic. Look at other equilibrium like liquid-liquid equilibrium and gas absorption and so on.